Okay, so here we are back to 6.1, approximating areas using Riemann sums. On this example number 2, if we would have added up that area, I went ahead and wrote after 5 minutes, the aquarium has 23.625 gallons in the tank. And I guess I probably should have put approximately. The aquarium has approximately 23.625 gallons in the tank. Okay? And, excuse me, as we would add the number of rectangles here, you would imagine that the error would be less because you can see what the error is going to be. Like all of this right here is error, that they're adding on that isn't actually under the curve. And then there's some missing right there, so a little bit of it evens out. But this ends up being an overestimate. And if we, reduce the size of the rectangles and made more rectangles and they were skinnier, you could see how we could reduce the error there. And so the definition of this integral is going to be the limit as the number of rectangles goes to infinity. And that's why it ends up giving us the exact area under the curve. So now we move on to 3 types of Riemann sums. So left endpoint, lower sum, inscribed rectangles. So if you can see that from the left endpoint, if we were doing from A to B, look at where our left endpoint is. That gives us a 0 rectangle. And here's left endpoint, we go over and then we calculate that one. Left endpoint, we go over, we calculate that one. Left endpoint, we go over, we calculate that. It's going to be an underestimate. You can see all of the area that was not counted when we did that. But this is called a left end lower sum inscribed rectangle. And you're just breaking it up into whatever, like if this was 0 to 4, this would be 1, 2, and 3, so whatever your A and B is and how many rectangles that you're choosing would be your N, and then that's how you figure out what the width of each rectangle is. But notice that you've got either this side or this side. You've got this side or this side, and you chose left, and you and you chose left, and you went over. You chose left, you went over. You chose left, you went over. You chose left, you went over. So that's how that one is going to work. Here, you've got left or right. If you chose right, then you're going over this way. And that's your area that you're doing. So you've got left and right. You chose right. This is a right Riemann sum. You got left and right. You chose right. There's your area. You've got left. You've got right. You chose right. So these are right-hand Riemann sum. So we call this LRAM for left Riemann sum. And we call this RRAM. And if we use the midpoint Riemann sum, we call it MRAM. And so for the MRAM, if like I said, if this was from 0 to 4 and this was like 1, 2, and 3, then this would be at 0.5 because it's halfway between 0 and 1. So you would find your function's value at 0.5 and you would go this way and calculate that area. This one would be 3 halves or 1.5. And so you'd calculate the function's value, you'd go that way, and you'd calculate that area. This one is 5 halves. And so 2.5 would be, you'd find your function's value, go left and right to make your rectangle and calculate that one. And then this would be 7 halves. So, you know, with MRAM, it's 1/2, 3/2, 5/2, 7/2 for this one. You know, so it does go with the pattern. You know, the pattern exists. Always, patterns are always in math. So take advantage of those patterns. They will help you. And those are the 3 different ways that we can use rectangles to estimate area. You can notice that on MRAM, it seems to be the one that gives you the best approximation. Because with RRAM, it's going to be an over approximation when you've got an increasing function. Okay, so increasing function. For some reason, this pen does not want to work. But if you have an increasing function like we have here, increasing function, increasing function, increasing function. So if you have an increasing function, how about if I write over here? Maybe that'll let me write over here. You are going to have LRAM is going to be an underestimate. RRAM is going to be an overestimate. And MRAM is really, we'll end up finding out that it's going to be LRAM plus RRAM divided by 2. Okay, so it's going to be a better approximation, and it's a very good approximation. But MRAM and LRAM, if you've got an increasing function, LRAM is an underestimate, RRAM is an overestimate. When you have a decreasing function, your LRAM is an overestimate, and RRAM is an underestimate. So it just changes depending on what kind of function that is. And they will ask you questions like this quite a bit about, you know, whether it's an overestimate or an underestimate. So now, definite integral definition. Let f be a continuous function on the closed interval ab and f of x greater than or equal to 0 for all x in the interval. Let the closed interval AB be partitioned into n subintervals of equal length. Delta x equals b minus a over n. Then the definite integral of f over ab is given by. And so look, it's the limit as n goes to infinity of the summation k equals 1 to n f of c sub k times delta x is equivalent to the integral from a to b f of x dx. So what this is the y value of the function times the width of the rectangle. Okay, so the y value of the function times the width of the rectangle. And so you really are just summing up. The only thing that why it's equivalent to the exact area under the curve is because you're breaking it up into infinitely many rectangles. As you take your limit, as n goes to infinity, the number of rectangles there, k equals 1 to n. And so our general solution method for inscribed or circumscribed rectangles with upper or lower sums: number 1, draw a rough graph of the function over the interval. Use the formula delta x equals b minus a over n, that's very important, to determine each sub-interval length. Compute the x-coordinate of rectangles at either left end or right end, and then compute the areas of each rectangles, inscribed or circumscribed, and then find the summation of the approximated areas of the rectangles. So example number 3, find the area A under the graph of f of x equals 1/2 x plus 1 on the interval from 0 to 5. So now, from 0 to 5, we're going to partition off. Oh, wait. Sorry, had the wrong color. We're going to partition off here and see how many rectangles we have. So from 0 to 5, these are actually trapezoids. 1, 2, 3, 4, 5. So we have 5 trapezoids here, okay? If we wanted to, instead of using LRAM, MRAM, or RRAM, we could use a trapezoidal approximation. And when we do that, we are using the area of a trapezoid formula. Height divided by 2 times base 1 plus base 2. And the bases are the ones that are parallel. So this would be, right here would be our base 1. Right here would be our base 2. It would be the next one's base 1, and then this one would be that one's base 2. And then this one would be base 1 for the next one. Base 2 would be this one. This one would be base 1, and then this would be base 2. And then this one would be base 1 for this one, and then we have base 2 here. If you notice right here, that is 1, right? That is the height of your trapezoid. Remember, the height of your trapezoid is the distance between the parallel sides, okay? That perpendicular distance between the parallel sides. So for every single one of these, my height is 1. All of my trapezoids have a height of 1. Because I'm imagining that I'm just taking this trapezoid right here. I'm just going to mark it. Look, there's my trapezoid right there. That's my first one. And the base 1 is the function's value at 1. Well, my function is f of x equals 1/2 x plus 1. So if I am, trying to figure out what that y value is, although I can clearly see that it's 1, I could make a little box over here, or chart, and here's my f of x, and I need to know 0, 1, 2, 3, 4, and 5. I need to know all of those y values. And so if I put 0 in, I get 1. If I put 1 in, I get 3/2. If I put 2 in, I get 2. If I put 3 in, I get 5/2. If I put 4 in, I get 3. If I put 5 in, I get 7/2. So you can see that my base 1 for my first one is 1, and my base 2 for my first one is 3/2. So if I wanted to, I know that they all have a height of 1. And I can say that the area is equal to my height of 1 divided by 2. And then this would be times 1 plus 3/2, because that's my base 1 plus base 2 for that first one that we shaded in green. And then plus, we've got 1/2. Now look, I'm going to use 3/2 again, and plus my 2, because this one is, my base 2 is 2. So this, again, the height of 1. So I put 1 over 2. And then this one is 3/2 plus 2 for my base 1 plus base 2. Now I do my next one, has a height of 1. I still have my 2 plus 5/2. Plus, next one, I have a height of 1. And I've got my 5/2 plus my 3. And the last one, I have a height of 1. I've got my 3 plus my 7/2. So you can see here that I'm just adding up the area of my trapezoids. This is a linear function And we end up, producing trapezoids. This should give us the exact area because it's a linear function. And so this gives me 1/2 times, this would be 5/2, plus 1/2 times, this should be 7/2, plus 1/2 times, this should be 9/2, plus 1/2 times, this one should be 11/2, and plus 1/2 times, this one should be 13/2. So that gives us 5/4 plus 7/4 plus 9/4 plus 11/4 plus 13/4. So we've got 12, 21, 31, 32, 42, 45 fourths units squared would be the area under the curve. Okay, and we used, they're saying use geometry. Well, so we used areas of trapezoids. So this formula right here was a geometry formula for the area of a trapezoid. And again, this was our height, right? For each one, that was the height of the first one. This is the height of the second one. I'll even do it in a different color. This is the height of the first one. This is the height of the second one. This is the height of the third one, height of the fourth one, and height of the fifth one. So, and then you saw your, what am I trying to say? Your B1s and your B2s, okay? And you could also write this as 11.25 units squared. All right, so error in Riemann sum. For the function shown at the right, draw rectangles forming the left-hand sum shaded in blue. Calculate the left-hand sum. Let delta x equal 2. Okay, so I'm going to get my blue pen out, and we are going to do an LRAM. So remember, if delta x is 2, that means I'm going by 2's here. So every 2, I'm going to draw my line. I could either choose my left-hand point or my right-hand point. Since they want me to choose my left hand, I'm going to go like this and go across and then down, because this is the rectangle that I'm going to calculate the area of. It's going to have a width of 2 and a height of 8, because that's my left-hand side. So if I want to find LRAM sub 3, the reason I say sub 3 is because there's going to be 3 rectangles when I'm done. I've got 2 times 8 for my first one. My second one, I use my left side. I go over and down to create my second one, and this is going to have a width of 2, and you can see that the height is 7. The last one has a width of 2. I've got my left. I go over and down to create my rectangle and shade it, and I say it's 2 times 5. I can see that my LRAM for this rectangle from 4 to 6 is 5. So this gives me 16 plus 14 plus 10, 30 plus 10, 40, and I do recognize that that LRAM for a decreasing function is an overestimate. Okay, so 40 is my approximation. Next, we're going to draw rectangles that represent the right-hand sum and shade them in red. So I'm going to get my red one out, and we're going to do RRAM this time. So between 0 and 2, the one that's RRAM is over here. I'm going to go over and shade. So you can see that that is a little bit of a different rectangle, but it still has the width of 2. So this is RRAM with 3 rectangles. And so it's still going to be 2 times. Now this time it's going to be 2 times 7. because I'm using the right-hand side, and that's at 7. So that was my first rectangle. And then I'm using the right-hand side here, and then I'm shading. And this will be my second rectangle, still has a width of 2, but I'm using the right-hand side, which is at 5. And the third one, it's the right-hand side is down here. So I will be doing 2 times 1 because I can see that that right side is at 1. So this is going to be 14 plus 10 plus 2, 26. And this is an underestimate because it's a downward decreasing function, and I'm doing an RRAM on a decreasing function is an underestimate. So which sum overestimates, which sum underestimates? So LRAM overestimates and RRAM underestimates. And now it says repeat steps A through C for the function shown at the right and let delta x equal 0.5. So if delta x is 0.5, we are going to break it up into 3 rectangles here. And we're going to do LRAM 3 in blue. So LRAM 3. Now, did you notice that every single one of these is 0.5? So we could put 0.5 on the outside and then just put our LRAM values, add them up. So I've got the first one is 1. Our second one is 4. And our third one is at 6. So this is going to give me 0.5 times 11. So 11 halves, or 5.5. And we can see that that is an underestimate because it is an increasing function. Now we're going to do our RRAM in red. And so we're going to choose the right-hand side and go over, and then we're going to calculate that. So we've got, and all of them are 0.5, right? They all have a width of 0.5. So the first one is 4. Next one is 6. And the last one is 7. So this is going to be 17 halves, or 8.5. And that is an overestimate. So now we're ready to fill out this chart here. We've got an increasing function, right? And let's say we're breaking it up like that. The left-hand Riemann sum is going to be an underestimate. Increasing function, right-hand Riemann sum is going to be an overestimate. That's with concave down. Concave up. With concave down, if we had a left-hand Riemann sum, it's going to be an underestimate. With concave down, increasing, if we had a right-hand Riemann sum, it's going to be an overestimate. Now, if we have a decreasing function but concave up, our left-hand Riemann sum is going to be an overestimate. If we have a decreasing function concave up, our right-hand Riemann sum is going to be an underestimate. And if we're decreasing and concave down, our left-hand Riemann sum is going to be overestimated. And decreasing concave down, right-hand Riemann sum is going to be an underestimate. So I gave you a little picture of what each one of those would look like. And basically, like I said, we're just taking the area of a rectangle and adding them up and giving an estimate